how many ICCFs have you done in your life, and what benefit did you gain from them?
This is my first ICCF, but I've been involved in another 10 workshops, mainly in Italy, but also in France. So one might say it's been 22 years since my first conference, and this is the 22nd ICCF. It's just a coincidence.
And have you gained benefits?
Well,
How would you
I've gained sacrifices.
Yes. Okay.
No, it's been a pleasure to serve this community, and we've come almost like a happy family, I would say, of scientists who meet almost every year, and we have new results, and we enjoy discussing them, and so it's a mixture of technical and scientific results combined with some social activities.
Very good. Dave Nagel, tell us about how many ICCFs you've done in your life, and what about the benefits you've gained from them, or what you see?
Well, thanks, Marianne. It's been my good fortune to go to all of these ICCFs over the years. Francesco Celani from Italy and I have that distinction at the moment. He will last longer than I will. He's much younger. But I was also able to co-chair 2 of these, and they've been a large part of my life. I'm in my 60th year of working. I've been involved in this field for 30 years, and Bill said it very well. It's a marvelous combination of technical, scientific, engineering, focus on one hand, and the development of friendships, people from around the world in academia and companies and all. So it's a gift in my life to have been involved in these conferences. Thank you.
And Mike Mckubre, same question to you. How many have you been to, and what would you say about your experience?
Well, it is, and the whole cold fusion exercise changed my life literally and transformed my research activity. I've attended every one except one of these conferences. And probably another, 25 conferences on this topic over the years. It's one of the advantages of being looked down upon by the scientific community is that it forms a very strong bond. So this is a really very fine group of people, some of the most intellectual and scientifically driven individuals that I've ever worked with in my life. So I enjoy coming. I had to come here all the way from New Zealand, so 24 hours of flying to arrive at this door. My 40th trip to Rome, mostly in pursuit of cold fusion activities. So it has become a very good part of my life. I'm looking very much forward to the activities this week, which have already begun.
Let's talk about this beautiful location we're in, which is Santa Maria degli Angeli in Assisi. Bill, first of all, can you tell us how you chose this and what was your impressions?
Well, actually, it was Claudio Pacci who suggested this place, and I came here last year to check it out, and I discovered that it's actually very famous all over the world, but it's not known to be famous because Santa Maria degli Angeli gave their name to Los Angeles in California. They were Spanish missionaries who went out, and of course they founded San Francisco as well. So it all started here. I like Umbria particularly because the food and wine are very good, the climate is perfect, the people are friendly. The hotel staff are very helpful. This hotel is the right size for our kind of conference. They have all the facilities in one building, so as we're getting all a bit older and not walking quite so fast, we can find our way around. In fact, this lecture theatre is on the ground floor, which is quite helpful for people, I think. This place happened to have all the right characteristics I was looking for.
Very good. And Dave Nagel, what was your impression upon coming here? What do you think?
Turn on the microphone. delighted to be here. This is a marvelous place, as Bill said, in all respects. And someone has even scheduled very good weather, so we're looking forward to an exciting week. This is very pleasant. Thank you.
Mike Mckubre.
I must confess to have not stepped outside the door of this hotel yet, so I'm sure I will find it spectacular. I'm told that the cathedral is quite fabulous.
Good. All right, well, let's go on to talking about the subject we're here for, cold fusion, LENR, CMNS. 30 years of it. You've all been here pretty much through the duration. So we say the fire is still lit. So from a strictly scientific point of view, what has changed in 30 years regarding our knowledge of the phenomenon? Could you each address that? We'll start with Bill.
That's a very difficult question, I think. Sometimes I'm a little bit embarrassed about the slow rate of progress. Back in 1989, Martin Fleischmann and Stanley Pons claimed excess heat, and they thought they had some nuclear signals which actually did not turn out to be quite correct. And that really started a kind of race to find more excess heat, to show that there was an abnormal phenomenon which needed some kind of explanation. A couple of years later, helium was shown to be a product of this abnormal heat reaction. But since then, there hasn't been a lot of progress, I have to say. So I'm a little bit disappointed that we still don't know definitely any one particular nuclear reaction which is occurring, and that's a disappointment to me. We haven't even shown that deuterium is consumed as a fuel. But we do know some products, and helium is certainly one of them. So it looks as if deuterium is fueling a helium-generating reaction or a series of reactions of some kind. But we are still in deep water as to know exactly how this is occurring and why.
Dave Nagel, I have the same question for you. And it would be helpful if all of you would also address what's changed, like in this time. You know, we certainly are things that we know have changed, that we know more about. But why don't you address this, Dave?
In a somewhat simplistic fashion, I divide the world up in this field to experimental and theoretical concerns. That is, laboratory evidence and true scientific understanding. And as far as the experimental evidence goes, we went from an uncertain situation, controversial situation in the early years to one where we now have what I assert is a bulletproof case for the existence of low-energy nuclear reactions. There is evidence for tritium generation, a very easy thing to measure. It doesn't occur in the environment. Many experiments have shown that you can generate tritium. Bill just referred to helium generation, which has been seen in many experiments, correlated with the heat at about the right level, right compared to the known energetics of nuclei. And then there are other reaction products. And then there's the heat, which has been measured with very good signal to noise in many, many types of experiments, electrochemical experiments, hot gas experiments, plasma experiments. So on the experimental side, I argue, much to the consternation of some of my colleagues, that we're in a very, very strong position. On the theoretical side, we still don't understand the basic physics of this field. And until we do that, then the scientific community more broadly, people outside of this field who are potentially interested in it, don't have something that they can sink their teeth into, read papers about ideas and equations and theoretical results and how they compare with experiments. So we have a mixed situation. It's strong and exciting on one side. It's frustrating and slow, as you said, Bill, on the other side. So that's one perspective on that question.
And Michael Mckubre, can you help us, because these are the questions that come up. So would you be so kind as to address?
Well, this field is built on the ideas and proclamations of an old friend and mentor of mine, Martin Fleischmann. I knew him when I did my postdoctoral work in Southampton. I knew Martin to be, at that point, one of the two top electrochemists in the world And yet the statement that nuclear effects could take place in the deuterium-palladium system was preposterous. So because I knew Martin, I gave him a 50-50 chance of being right, and I diverted some of the funds from my sponsor at the Electric Power Research Institute to an experimental test of whether this, whether my old friend was crazy or not, actually. And as luck would have it, we discovered a thermal effect which could not be explained by chemistry or energy storage or any other known conventional process, and could only be nuclear because of its scale. That was in 1989, and I diverted my entire research activity and half of my research group and essentially all of my focus to pursuing that activity, and did so with more or less single focus for nearly 30 years. I retired a couple of years ago, but still I'm heavily involved. So David's correct. And the experimental evidence for the existence of low-energy nuclear reactions is essentially overwhelming. You know, I'm as confident that there is an excess heat effect in the deuterium-palladium system as I am that I am sitting here talking to you now. I could be hallucinating, but the chances are slight. As Dave says, the theoretical situation is less advantageous, in part because I think there's something that we don't fundamentally understand about nuclear physics. I think that we're going to have to change something in nuclear physics in order to explain what it is that we have seen. And I once was summoned, I suppose, to Edward Teller's door. Edward Teller, the father of the hydrogen bomb and the preeminent physics thinker in the United States until his death a few years ago. And what Teller said is that if what I was saying to him was correct, that he could explain it very simply with small modifications to the laws of nuclear physics as he understood them, and this was the man who had established a good fraction of the laws of nuclear physics, and that it would turn out to be nuclear catalysis at an interface. I somewhat intimidated by this man. I didn't challenge him on that, and I didn't ask him what he meant. I chastise myself to today for not probing more deeply, because I think what he said to me is exactly what's going to turn out to be true. There is a nuclear catalysis that occurs at an interface in a specially prepared space, and our inability or occasional inability to reproduce the effect is that we simply haven't created the zones, the spaces on the surface which facilitate this nuclear reaction. So, I'm going to chastise the community tomorrow somewhat by our poor communication skills. And inside the community, it is very clear that there is a nuclear effect. We don't quite know what the nuclear effect is, but it's an effect that can only be nuclear in that it produces nuclear products. You can't make nuclear products by chemistry. But we have not communicated that information very accurately, very effectively outside the community, and we really need to pay much more attention to the outside world.
All right. The results of the cold fusion experiments are still defined as controversial. Do you agree with this definition, or do you think that's a result of prejudice that has accompanied this kind of studies? Bill, why don't you talk about it first?
Well, of course they are controversial, but I don't think they deserve to be controversial. I think the quality of experiments in general, when they're performed by scientists rather than by garage researchers or by get-rich-quick engineers, I think some people might know whom I could be talking about, so I've got to be careful. No, I think that the science, when it's done scientifically, has been extremely good. So
follow up on that, because people from the outside world, people who don't deal with this community the way we do all the time, really don't have an idea of the quality of the work in research you're talking about. Could you throw out some examples of those?
Well, let's suppose you were a skeptic and you thought that there was some doubt about excess heat, for example. Now, that was the common rejecting philosophy of 1989. Well, a couple of years later, they showed that, Miles showed at China Lake, that helium was produced in the expected quantities for one of the proposed reactions. And so there were two completely different measurements, the heat and the helium, and they both supported the same explanation. So even if you had doubt about one of those, the fact that the other supported it confirms that the general direction of the hypothesis was correct, that there was a nuclear reaction going on involving deuterium and producing helium.
Dave Nagel?
Well, it's safe to say that the field is still controversial because of the bad start, which is remembered by many people despite the 30 years that have passed. But I say, rather than being a prejudice, I view it as a matter of ignorance, as ignorance. It is being ignored by the scientific community. The data from these many experiments, thousands of experiments, hundreds of which have produced solid results that are documented in good papers, some in referee journals, but many of them on the internet. If people paid attention to that, they would see that there is no way to get rid of all of those results. In other words, one has to accept the reality of LENR and its characteristics if one is willing to stop and look at the literature. But people in general are not doing that because the field has not yet achieved a legitimate membership in the scientific community. And lacking that membership, lacking recognition, we don't have respect and we don't have resources. So younger people and academics, even people who hope to get rich on this, are reluctant to dig into the available information, and it's understandable that they're reluctant. There's no motivation other than intellectual curiosity, which brings many of us here, but there's that barrier. So I view the situation as one in which we are being ignored at a time when there's a mountain of available information that could change this field very quickly. Thank you.
Dave, before I move you off that question, do you mind throwing out some examples of the high quality research, the researchers, where they're from, what they did, even just quick bullet points, just because I don't think the whole world outside even has an idea of the caliber of intellectual firepower that's been working on this.
Yeah, Bill mentioned the correlation between heat and helium started by Miles. I think there are 16 papers now that report both effects and their correlation. I will happily turn to my colleague on the left here as having done, 100,000 hours or more of high precision calorimetry, that while it didn't result in large energy gains, had very, very good signal noise, it was bulletproof information offered in multiple conferences, as Mike said, in papers that were following them. Very, very good work. Here in Italy, the work by Vittorio Violanti and his colleagues is similarly thorough. Work at some small companies, Coolescence comes to mind now. Very, very thorough research work. So I think if I had prepared for this question, what you just asked, I could rattle off maybe 20, but they're out there and they're readily available.
Michael Mckubre.
Well, I'm going to demur slightly from my esteemed colleagues. I don't think we're being ignored. I don't think we're communicating very effectively, but I don't think we're being ignored, and there is no stigma anymore. If you talk to a scientist under the age of about 45 that was not around at the original press conference and the highly polarized rhetoric that came out of that conference, if you weren't exposed to that experience in 1989, then you are not contaminated, and the scientists that I talk to who are younger are open-minded, fresh, simply keen to pursue the science objective. I was involved in an exercise recently with Google, the Google Corporation in Mountain View in California, just down the road from where I was living. Spent a year with the Google guys. I know the biggest problem Google has is they make $2.2 billion worth of profit every month, and they have to spend that wisely. And Google had determined that the biggest problem that the world faces is the source of primary energy in the future when the fossil fuels run out. The renewables cannot possibly carry the load. Man needs energy. Where do we get our energy from? The conclusion at Google was that this has to be a nuclear source. Of the nuclear sources that were available, there is hot fusion, there's cold fusion, and there's advanced fission. So Google put money into all three. They put money into a cold fusion activity, have plowed $10 million into it, have brought young academics to the field. They've put in a good deal of work without prejudice, without belittling the work that was previously performed, and attempting to learn from it. So far, they haven't reproduced the more significant parts of our findings, but they will, and they will continue, they will proceed, they will provide scientific support for the activities, inevitably. And most importantly, they're bringing to the field the one thing that we desperately need, that is youth. We need to get young people involved. The young people are interested, they're motivated, they're enthusiastic, and quite frankly, the reason I persisted with this for 30 years is it is the most important scientific subject that I could possibly make technical contributions to. If there may be other more important topics, but I don't have the skill set to handle. But of the things that I know and know how to do, I could not possibly be working on anything that is more important. And this is the feeling amongst a good fraction of the younger generation of scientists. So I'm highly encouraged. I don't think money is going to be a problem. I think once we communicate effectively to the outside world, following the footsteps of Google and others, there are other major corporations who are involved also, I view the future as extremely rosy.
Dave Nagel.
I agree with the future view that Mike just expressed. This field will triumph in the end and be very, very important to mankind. Much of the basis for my statement about being ignored is born of interacting with the Department of Energy in the United States, the Department of Defense, a major user of energy, and other parts of the government. And they're simply unwilling to fund the kind of research that the large companies that Mike cited, are Google in particular, now funding. So what I call ignorance is not absolute, but it is very, very broad, and to the detriment of the development of the field. We can't bring to bear the synchrotron radiation, the neutron scattering facilities, and other things that are available in the U.S. to promote the understanding of the materials that are fundamental to this field without getting those agencies involved. And I know I'm speaking from a U.S.-centric viewpoint, but the situation isn't that much different in most countries, and that's, I say, where I'm coming from. So thank you.
I'd really love to talk more about those points, but I know we're limited. Well, let's just say, let's go back to a couple more basics, which could you explain in a few words what LENR means? And also, what do you see as the prospects of moving from pure research to research applied to industrial and domestic use of cold fusion? Let's ask Bill Collis first.
Well, I always think it's premature to put a name to cold fusion or low-energy nuclear reactions or condensed matter nuclear science when we haven't quite yet identified those reactions. So there's a tendency, we have to call it something, we think we know what it means, but it's not properly defined. I think the best example we have of very well-known low-energy nuclear reactions are, of course, the fission reactions which are induced by low-energy neutrons. And we understand that very well. And there are some models for cold fusion which follow this model in some ways, for example, the exotic neutral particle models. But they're not accepted. But it's certainly a good definition. No one can say that low-energy nuclear reactions don't exist, because you can always point out conventional nuclear fission. As for the prospects, in my opinion, in the political sense, as we can propose cold fusion as a remedy for global warming, for the depletion of fossil fuels, which are certainly going to run out one day. And it's terrible to think we're burning such fundamental resources just to create energy when there might be some much nicer, cleaner alternatives. So the prospects I see of resolving a lot of political and economic questions, maybe energy will come down to a much lower price because the fuel is extremely abundant. If we assume that the deuterium in the oceans is the fundamental fuel of cold fusion, which is quite a reasonable assumption, then the oceans would last 1 million years. And if, as others suggest, that it's actually hydrogen, protium, in the oceans, that would last well over 1 billion years. Well, the Earth won't last that long, because all life will die when continental drift and subduction of sediments stops, because there will be no carbon dioxide left in the atmosphere for plants. And we could go into a lot of details to why life won't last that long. But whatever, we will never run out of energy. We'll probably find another planet to go to or something like that. So,
All right,
thank you.
Dave Nagel. A few words about what LENR means and the prospects from our moving from pure research to research applied to industrial and domestic use.
On the terminology front, I will spend more than a few words. The moniker condensed matter nuclear science is almost certainly appropriate, because of what we have to bring together experimentally in order to observe the effects that have been seen many times and reported. The terminology low energy nuclear reactions, I believe, is also accurate. And in my view, cold fusion, that is a nuclear reaction that results in two nuclei forming a single nuclei, is a subcase of low energy nuclear reactions. So that doesn't help solve the terminology problem, but I think that the low energy nuclear reactions moniker is A, appropriate, and is B, going to last. Now, as far as commercialization goes, I'm very upbeat on it. A summary of the experimental work to date is that it is possible to get more energy out thermally than you put in electrically. So if you put 1 unit of electrical energy, you get 5 or 25 or even more units of thermal energy out. So think of that in terms of the cost of energy. It could have a dramatic effect on lowering the cost of energy. Oh, and by the way, while these low-energy nuclear reactions are happening, you don't have prompt dangerous radiation as you do with hot fusion or fission. And you don't have radioactive waste left afterwards. And they don't generate greenhouse gases. And they have the prospect of being small units that could be put in homes in small buildings where you could get maybe a few kilowatts out of something less than a meter cubed. So for many, many reasons, remarkable reasons, each by themselves, but all taken all together, I view it as a certainty that this will be commercialized. And I view the field as being now where the transistor was maybe 70 years ago, shown to be a real effect, but not yet turned into integrated circuits that have led to the computer and communications revolution that we enjoy. So it won't happen during my lifetime. It's going to take at least a couple of decades because of the time it takes to produce products, first prototypes, then products, get regulatory approval, consumer acceptance. There's a long ways to go, but I am willing to bet my grandchildren's income, let's say, that this is going to be very, very important in the longer history of humankind.
I just want to expand on that a little bit. Our thoughtful co-chairman Claudio has come up with some of these questions, and I have some of these questions as well. So Dave, you said 20 years. Do you, because people come to us and they really are like, this has been going on for so long, you know, they don't really have the kind of historical perspective of the work that you can offer. Could you point to major points if you were trying to really make a case right now of saying this is what will happen, this is exactly what we're concentrating on now, and where it will go, and a time frame?
Yeah, so that 20 years is to having a product on the market. And for that to happen, we must have control, reproducibility and control. Imagine your automobile that turned itself on and went whatever speed it wanted to go, the way the Ellie and our experiments often do. We must be able to turn it on, turn it up, maintain it, turn it down, turn it off, repeatedly and controllably. Okay, so we're not there yet. And then once we get to that, we have to build a prototype of a product, something that actually works, can be tested to see if it's reliable, see if it lasts. Okay, and then you go from the prototype stage to the product stage in-house. And then you go to what's called beta testing. Other people start to use the same thing. Okay, and then you finally have something that you can take to the regulators and say, okay, fine, it's nuclear, but it's not dangerous. And they'll go through tests and so forth. And eventually, consumers will or will not accept these. Now, I'm of the opinion that at that point, they will, the acceptance, the consumer acceptance will be ready, even greedy, because here is a safe energy source that you can have in your home that can be refueled on a 6-month basis, every 6 months with a small amount of material, okay, and run reliably, reproducibly, controllably for long times, okay, to produce heat and also electricity. If you make enough heat, you can make electricity. Okay, so I am very bullish on it, but I think there's a realistic timeline involved that is unavoidable.
All right, let's have Michael Mckubre discuss these points for us.
Well, the claim that Martin Fleischmann and Stanley Pons made that fusion effects or something simulating fusion effects occur inside a metallic lattice, hot fusion, it's a big claim. I didn't believe it. I gave it a 50-50 chance, as I said, but set out in the laboratory and demonstrated with my own eyes in my own laboratory under my own control that in fact does occur. Fusion-like reactions occur in the deuterium-palladium system. But as big a claim as that is, and as bigger consequences that observation is, what Fleischmann and Pons discovered is vastly greater. What they discovered is condensed matter nuclear science. Nuclear processes take place in metallic lattices and potentially other condensed matter systems by means, at rates, and with product distributions different from the way those reactions occur in free space. This is a huge statement. And nuclear physicists believe that they can ignore the surrounding lattice, that chemistry doesn't affect nuclear process. What we have shown is that the lattice is critical in determining the rate of reaction and the products of reaction. This is not surprising. In 1991, Julian Schwinger, who was the prince of solid-state nuclear physics, got his Nobel Prize with Feynman in 1964. Schwinger said that unlike the near vacuum of hot fusion, the ambient environment of cold fusion is the lattice, which is a dynamical system capable of storing and exchanging energy. The fact that it occurs in a lattice changes the game, changes the process. So what we have found is an entirely new way to conduct nuclear reaction. And the power of nuclear reaction is of significance. The energy density of nuclear processes is something like 10 million times greater than the energy density of chemical processes. So a nuclear battery would have 10 million times the energy density of your conventional batteries, and just the scale of the difference. In a laptop that never runs out, a car that needs refueling once every 3 years. And the fact that this is potentially possible, I'm not going to claim that it is, I'm not going to claim that we can do that now, but we certainly have opened a door on that possibility, and it absolutely needs to be pursued.
Very good. I want to ask the three of you, because we've been talking about all these things, when you walk out of here, are there some things in particular that you wish we had got to or that you want to emphasize? Bill, do you want to start?
I'm not sure if I have anything to say about that.
All right. Well, I know Dave and Mike. So, Dave?
Well, I have a very simple-minded view of this field needing three things, and they've been touched on already. One is recognition and respect and resources. That's one. Secondly, scientific understanding. If we understood the theoretical mechanisms behind this field, we could design experiments, we could achieve reproducibility, we could achieve controllability, I believe. So that scientific understanding, the second thing, is really critical. And then the third is commercial exploitation for the good of mankind. We must see this through. I say we very broadly, many people, engineers, business people, who are going to get to a point where one can buy this the way one buys batteries. Okay, so I say recognition, legitimacy, scientific understanding, and commercialization are my summary of the needs of the field.
And Michael, I was really glad you talked about Julian Schwinger, and really here's a point of what is going on in this field. Here's the unique distinction. Are there other things, because you're so practiced in having people come to you and really having to do overviews, and you've done it well. From that to another example that comes to my mind is when you talked about the note that people don't remember from the original paper of Fleischmann and Pons being omitted from the consciousness of the general public. Can you help us with other particularly salient points like this to just drive home what we're trying to do?
That's a big burden. No, I think we as a community need to recognize that we've done an appalling job of communicating to the outside. We need to do better. We also need to recognize that there's a lot of science to be done, and these observations of an effect are of sufficient number and of sufficient diversity to indicate that there's a huge space out there which needs to be plowed, and an awful lot of science that needs to get done. And one of the things that very much encouraged me about the Google activity is they put money into doing science. We just brought young people together, by young people I mean people in their 30s and 40s, which looks looks young to some of us, right? To do science, to do good science. So if we could just vector some attention towards the underlying science of nuclear processes in condensed matter, I have no idea what the consequences of that research will be. I have no idea what the products will be. I will say that if the only thing that we ever do with our field is to learn how to make hot water for people to run showers, I shall be severely disappointed. I think that the potential of wielding the power of nuclear physics on a tabletop is much, much greater than that. I don't know where it will go. I don't know if I'm going to be around to see it, but it has to be pursued by scientific methods, using scientific principles, with some stability and some good guidance. And we haven't, we've been a little bit scattered as a community. Everybody has their own idea. And one of the horrors of working in this field is that as soon as anybody thinks they've succeeded, they stop talking because the prize is so great. Nobel Prize or $1 billion corporation. So we got to think in terms of science, and we got to think in terms of energy source for mankind. So that's where I would like to encourage us to go. Thank you.
Well, thank you all very much, and we look forward to this week and how much further things go.
Okay, thanks, Guy. Thanks, Bill. Thank David. Thank Michael. And tomorrow we start at 8:30 with ICCF22, and I hope that this was great conference, important for the future of this kind of research. And we wait news about many people that will speak in this table. Thanks.